Hi, this lecture is on Lakehouse. So, the first generation of platforms for business intelligence was a data warehouse where you had structured data and you had this ETL, which was pulling from structured data, and you had BI and reports on top of it. The main intention was structured data. The next generation came with a data lake, and what you would do is that you have structured, semi structured, and unstructured data, and then you had ETL, which was going into the data warehouses, and from the data warehouse, you had BI and reports, and from the data warehouses, you can also do data science using Python and R, but the main objective was to dump the data in the data lake without any transformation. And you can do data science on it, you can do machine learning on it. So there was no schema enforcement. Usually it is treated as warm. Write once, read many has support for R and Python, used mainly for data science, has streaming support. SQL can be done, but it can be a little bit cumbersome because it can be slow and because there is no update functionality there in the data lake. So there are a couple of challenges that came into picture. The first challenge was reliability because you had to get in data and then there would be some ETL, you get into the data warehouse. So there are two steps in it, and there would be data stillness because there is a time gap between the data being received in the data lake and then into the data warehouse. And the data warehouse had limited support for advanced analytics, and obviously there was a total cost of ownership being increased due to maintaining the data warehouse and the data lake. So you had the data lake, you had the data warehouse. So this is what is the data lake architecture, which is prevalent in most cases, and we see the challenges. What happened is apart that you the SQL could not be run, meaning you did not have the insert updates on the data lake. So, and moreover, the philosophy was to dump all the data. Unfortunately, the data lake became not a lake, but it became a data swamp, and there was question about the quality and the schema governance and all these factors of the data lake that was quite not really good. So next generation of platforms is a lakehouse platform where you have the data lake and then you have metadata, caching and indexing layer on top of it, and then it is much more simplified and you could have BI, reports, data science and machine learning on top of it. So this is something great about the Lakehouse platform. Now, this metadata caching and the indexing layer had transaction management, governance, versioning, and auxiliary data structures. And you had metadata APIs, and which would also expose the SQL APIs and also the declarative data frame APIs from Python and R. Now, the SQL performance is of importance for the Lakehouse, and how it can be done is that if you cache files from the cloud object store on faster storage devices such as SSDs and RAM on the processing nodes, and moreover, the cache can be in a transcoded format so that the query engine can run efficiently, like the cache at Databricks partially decompresses the Parquet data it loads. Moreover, there was this auxiliary data in which the column statistics for each data file in the table was stored within the same Parquet file to store the transaction log, which enables data skipping optimizations when the base data is clustered by particular columns. We are also implementing a Bloom filter based index. So, as we are saying, this is from this paper, the CIDR Jan 2021 online paper by Ambas, Gotsis, Zin, and Mate. But I have seen that Databricks has implemented the Bloom filter. So, let's see what is a Bloom filter. It is a very space efficient probabilistic data structure, and it's used to test whether an element is a member of a set or not. False positive matches are possible, but false negatives are not. In other words, a query returns either possibly in set or definitely not in set. Bloom proposed a technique for these applications where the amount of source data would require an impractically large amount of memory if conventional error free hashing techniques were applied. So I've given the reference also. So what is a Bloom filter? It is like, do you have a key? The answer is no, and it is correct. Do you have key 2? The answer is yes, and there you have a necessary disk access and it gives. And you have key 3, it gives a false positive and it says yes, but it is actually no. So that's the thing that about the false positive in the Bloom filter that is there. Now, SQL performance is also improved in the Delta Lake by using Z ordering, which is a technique to co-locate related information in the same set of files, and it dramatically reduces the amount of data to be read. And this is the reference of the Databricks hyperlink, which you can see. And usually you would do a Z order in a column which is high cardinality, that is a large number of distinct values. Now, we discussed about the limitations of the data lake. Now, what we will do is that the Lakehouse implementation, you can implement it via the Delta Lake, which has a lot of facilities, and we will actually go in depth with a Delta Lake with a separate case study. But the things which are there, like it enforces schema, like if the data, if you can create a table just like in SQL, you create a create table, and you can have schemas, you can have constraints on it. Moreover, it gives you the ACID compliant. It supports time travel, that means versioning is maintained and you can go back to versions. And the most important thing which I love is that it supports upsearch, that means you can update and insert data, and you can do fine grained security control. So that's it about the Lakehouse. Hope you like the lecture. Thank you.